That was weird. I got kicked off there for a second. I think everything is working now, though. Sorry about that. So, let me just go over what I was saying before. Welcome to the live Q&A. Today I'm going to be talking about the humic and fulvic acid fertilizers from Bokashi Earthworks, the different formulations, how they operate as a biostimulant, and I'm also going to go over the different aspects of both humic and fulvic acid. And then once I'm done, I'll do a Q&A section. You guys can ask questions, even if it's not related to humic and fulvic acids. I'm here to help you guys with any of your growing questions. So, I guess we'll just start off with how these things are actually produced. So, I don't have a sample of it, but what we use is lignite. You've also may have heard it be called leonardite before, but it's an organic material that's been decayed into a mineralized form, and trapped in that mineral matrix is all the plant nutrients, macronutrients, secondary, and micronutrients. It also contains a wide range of different carbon compounds. Specifically, the ones that we are looking at are humic and fulvic acids. And so Dr. George from NASA Agricultural Technologies developed a process to take that leonardite, that lignite material, micronize it, and extract all of the nutrient ions and the humic and fulvic acid, all the humane or the organic stuff that's not soluble, the insoluble organic stuff is separated. It's called humane. It's separated from the humic and fulvic acid fraction. And it is, during this reaction in catalytic conversion and stabilization process, all the nutrient ions that are liberated from that material all bind onto the fulvic acid, and it chelates it. So chelation is a process in which nutrient ions are bound to carbon molecules to keep them in a bioavailable form that the plants and both the biology can metabolize. So what we end up with is humate fertilizer, and we have three different formulations that we sell. We have a high nitrogen formulation, and this is for used for leafy greens, for things like house plants, for vegetative phase of growth for a lot of plants. We have a product that is complex humate, and the complex has an even range of NPK. So the N humate is, if you look at that, it's 12% nitrogen, 9% phosphorus, 5% potassium, and then it also contains 45% fulvic acids and about 1% humic acids. And we'll explain the difference to those in a little bit. The complex formulation is 9% nitrogen, 9% phosphorus, 7% potassium, so it's a little more balanced of a formulation. It also contains almost 45% fulvic acid and almost 2% humic acid. And the complex formulation is for, I use it for a lot of my house plants around the house because it's just an even distribution of NPK. It's for plants that are in a transition phase, and those are the types of crops that I use it for. They can also be used for, a bunch of different wide variety of commercial crops like tomatoes, peppers, things like that. And then there's the high potassium formulation, and this is 6% nitrogen, 12% phosphorus, 10% potassium. Again, it also has almost 45% fulvic acid, almost 2% humic acid as well. And this is a high flowering, so this is a high phosphorus, high potassium formulation. And this is actually one of the most popular products that we have. A lot of people use it as an additive or as a standalone just to make sure that the plants have enough of the phosphorus and potassium that they need earlier on in the flowering phase to create those nice big beautiful blooms. So those are the three different formulations that we have. Now, I wanted to get into the difference between humic and fulvic acid. So, humic substances are complex, heterogeneous mixtures that are formed through the decomposition of decaying organic matter, such as plant and animal remains. They get essentially compressed over time, and you end up with this mineral, this organic carbon based mineral. And in that substrate is high levels of both humic and fulvic acid. Now, humic and fulvic acid are not the same thing, but they're oftentimes referred to as the same thing, but they do things vastly different from a metabolic standpoint when it comes to the microorganisms, and also from a biochemical standpoint when we're talking about soil chemistry. So, and they're also, humic and fulvic acids are actually classes of, carbon-based molecules. And I'll give you an example. So acetate, or what you find, acetic acid, which you find that in vinegar, that is actually a fulvic acid. So there's a bunch of different types of humic acids and fulvic acids, and they are basically defined by their molecular weight. So fulvic acids have a low molecular weight, usually between 500 and 200 Da, and humic acids have a much larger molecular weight. They're much more complex carbon chains, usually at 3,000 to 30,000. So fulvic acids, because of their molecular size, they're soluble at all pH ranges. So from 1 to 14, if you have a nutrient ion that is attached to fulvic acid, it doesn't matter which pH range it falls into, it's still metabolically available for plant uptake. Humic acids are soluble. They have they're soluble below pH of 2, but they're insoluble above a pH of around 6. So you need, they become more soluble with a higher pH range, excuse me. Oh, and also, if you guys want to look at the scientific overview that I printed out, I put this all together, there will be a link for it. You can either hit me up on the DM or whatever. I put this in my Dropbox. So, fulvic acid has a solubility across a wide range of pHs, and humic acid, it has a solubility at neutral or alkaline solutions. So anything above 6, but also it can be soluble below 2. So it's got to be really, really acidic. And again, fulvic acid remains available at all pH ranges. And then there's what they actually consist of are different chemical functional groups. So carboxylic acids, phenolic acid, ketones, alcohols, and aromatic compounds. And what they do is things like humic acids, which create larger molecular chains. What they'll do is they group together. You can kind of think of them like Legos, where you can kind of stack things together to make different things. And so they create these long carbon chains, and attached to these chains are spots where nutrient ions can basically be housed. They're kind of like parking spots for nutrients, right? And so when it comes to the difference of like the biochemical functions in soil of humic versus fulvic acids, so humic and fulvic acids, they both form stable complexes with micronutrients like iron, zinc, manganese, copper, and calcium, magnesium, any type of metal alloyed ion, which is going to be basically any of your base cations, as well as most of your micronutrients. And in some cases, they'll also be complex with phosphate, nitrate, ammonium, sulfate as well, depending on the configuration of those molecules and the charge on those different sites. Fulvic acids have a lower weight and a greater motility, so they actually have the better capacity to move nutrients. And so when things are attached to fulvic acid, they're carbon chelated with fulvic acid, they're going to be able to move not only just through the soil system, but into the plant much more efficiently. And one of the things is when these things are attached to the fulvic acids, it neutralizes some of that charge associated with nutrient ions, and so they can both be passively transported through mass flow in solution, and also they can be passively transported through diffusion. The plant doesn't have to expend any energy to uptake that nutrient that's attached to fulvic acid molecule. They chelate the nutrients more efficiently as well. So the fulvic acid has a higher affinity for micronutrient ions or nutrient metal alloy ions than humic acid does, and so it binds onto those, and again keeps them in a bioavailable form. And they also act as a fuel source for from different microorganisms in the soil system. So because they're low weight organic compounds, microorganisms that utilize carbon, any type of carbon substrate for fuel, can catabolize these well, also for their carbon, but also for the nutrients that are attached to those fulvic acids. And just like plants, and just like the benefit for plants, the carbon chelated nutrients are more efficiently utilized by the microbes as well. I'm just going to run through some more of this stuff. Oh yeah, and one of the things that they also do is they act to improve soil pH buffering, which is another thing. So when you have, let's take a modified growing mix and you're using a peat-based substrate. Peat is naturally acidic, and when you have a lot of carbon in the system, it slowly becomes more and more acidic because they're producing organic acids and enzymes, and over time the plant's taking up cations and decreasing the pH of that soil. So humic and fulvic acids can also help regulate the pH of soil. And then the difference between the two as far as the soil biochemistry, I'm going to get into humic acid now. So humic acid, with those longer chain molecules, what's happening is they're able to essentially improve soil structure, right? Because they're creating these long chain carbons and creating space. They're creating greater surface area along surface areas of the soil colloids as they widen those spaces out. They also act to house microorganisms as well. So microorganisms can utilize the fulvic acid as an energy source, and humic acids will actually hold on and basically house microorganisms. Now, the improvement in soil structure that comes from using things like humic acid comes from a couple of different things. It comes from both an improvement in soil structure. When you improve soil structure, you also get, again, that cascade effect of better water infiltration and better water retention. When you improve soil structure, you also get better gas exchange, so that way any of the carbon that is in that soil can be both exchanged from the decomposition of organic matter and can also be consumed by photosynthetic microorganisms that are in the soil from CO2 in the atmosphere. Humic acids also improve long-term nutrient use efficiency. And one of the reasons they do this is because they increase the cation exchange capacity, or the CEC, of soil. So the different types of soil will be able to hold on to nutrient ions more efficiently. In the case of something like a sandy soil, well, there's not a lot of organic matter, there's not a lot of clay or clay colloids to hold on to nutrients. Those nutrients go right through that soil. That soil doesn't hold it. When you add in humic acids, those long chain carbon molecules will actually grab on to nutrient ions for long-term storage. So while you get immediate availability of carbon chelated nutrition with the fulvic acid, the humic acid will actually hold on to nutrients for a longer period of time and will release them over a slower period. So you get basically increased fertility over the long term with the humic acid. We talked a little bit about them acting as a carbon and energy source for microbial communities. They also promote beneficial microbial populations like the Trichoderma, Pseudomonas, Azospirillum. All of those different types of microorganisms can utilize these types of carbon compounds for fuel sources, especially things like the purple non-sulfur bacteria. They're the photosynthetic bacteria. They can use CO2, and they can also change their modes of metabolism to acquire soluble organic compounds for energy. Humic acid also binds with ammonium, NH4, phosphate, and potassium, improving retention in things like sandier soils that leach. So not only do they hold on to, both the metal alloyed ions, but they also hold on to some of those negatively charged nutrient ions, those anions. All right, another benefit of humic and fulvic acids, specifically fulvic acids, they can cross plant cell membranes via endocytosis or diffusion due to small size. They also stay soluble in solution. So again, it improves the efficiency and the regulation or the metabolic ways in which the plant can uptake nutrients, because there's three ways, right? There's mass flow, there's diffusion, and there's root inception. So mass flow is the transport of any nutrients in water. We also have diffusion, which there can be active diffusion or passive diffusion. Active diffusion requires the plant to use energy, but when they're attached to fulvic acid, they can do passive diffusion by bypassing the need for that plant to expend energy to uptake those nutrients and those organic compounds. Also, these carbon compounds can often be reutilized for other things in the plant. They can be catabolized for energy, and they can do some other things in plants. And one of the things too is if you're using beneficial microorganisms that are colonizing, let's say they're colonizing, not just the roots, but the xylem, the transport mechanisms, and you're getting biochelated nutrients to the microorganisms that are living and working synergistically inside of the plant, it's a way that you can promote that symbiosis, because the microorganisms will also have access to those carbon chelated or those carbon complex compounds. Also, fulvic acid enhances ATP production. So adenosine triphosphate, which is the biological exchange currency for all cellular or biological mechanics, improves and enhances the production of ATP via stimulation of the electron transport chain in the actual mitochondria of the cells. They also both have humic and fulvic acids have antioxidant activity, where both humic and fulvic acid increase expression of antioxidant enzymes, protecting against oxidative stress. So sometimes when the plant is kicked into overgear, or sometimes when it's under stress responses, it'll create these oxygen reactive species, which essentially, if you know about oxygen, it can, like things like, let's take H2O2, hydrogen peroxide. It can be very caustic and it can degrade things. And so it does that internally, cellularly. So these oxygen species can degrade cellular compartments and rip cells apart if they're not neutralized by these antioxidant molecule. So these antioxidants can capture those oxidative species and neutralize them and keep them from harming the plant. Excuse me. Another one of the things that they do is metabolic enzyme activation. So they activate nitrates, the nitrate reductase, and which is the NR and the H plus ATPase, which is what helps regulate nitrogen uptake and assimilation. So the plants have to go through a process where ammonium is usually converted into nitrate through, microbial metabolism. That nitrate is taken up inside of the plant, and then the plant converts it back into ammonium, and then that ammonium is converted into amino acids, and then those amino acids are converted into proteins. And so all of this takes a lot of energy, and it can help mediate some of the enzyme activation, so it can decrease the energy needed for this complex metabolic process. It also helps increase chlorophyll content and photosynthetic rates. Plant growth and enhancement and yield enhancement. So numerous field studies showed increased root biomass and shoot dry weight, enhanced nutrient density in crops. One of the benefits of the humate fertilizer is when you're decreasing the amount of energy the plant has to utilize to uptake the nutrients, and when you always have something that's biologically available, the plant will store more, and also it will store more of those nutrients internally. And when we're talking about things like produce that we're putting into our bodies, when you have higher nutrient density, you're going to get more health benefits, because it means more iron, it means more calcium, it means more protein, it means more amino acids. And so it's not just about the yield increase when we're talking about things like growing potatoes or tomatoes or cucumbers or whatever that is. It's about all of the bioactive compounds that those fruits and vegetables are producing that are also going to have a beneficial effect. Not just the nutrients, but also, again, some of those other chemical compounds, things like lycopenes, things like carotenoids, things like, anthocyanins, beneficial antioxidants, and things that are healthy for ourselves. Also, there's been studies that show that the yield can be up to 20 to 40% with the use of humic and fulvic acid in crop production. And the reason why they show these results is because, one, you're getting increased nutrient use efficiency. That's one of the biggest things about the humate fertilizer is the efficiency. So the amount that you would have to use versus any other product on the market is typically much less. You might only be watering once or maybe twice a month versus having to feed something daily. So the use efficiency, the amount that actually stays available and makes it into the plant or that's utilized by the microorganisms in your system, is 96%. Conventional salt-based or chemical fertilizers have about 15 to 20% use efficiency. So it has a higher use efficiency, which means you can use less and get the same results. And again, we're mitigating the negative environmental impacts, because if you were to take, let's say, runoff, if you were growing in a hydro system, you had runoff, and you took that carbon chelated nutrition and you put it into a field, it's not going to acidify that. It's not going to make that soil worse. It's going to start improving that soil by adding in that carbon, stimulating that microbiome. And then also, that's with so much fulvic acid in the product, what's happening is anytime that you have nutrition that's in a soil, it's going to go in there and it's going to help bind to the things that are already there, increasing the efficiency or the fertility of the soil substrate that you're using, or the native soil that you're using. So the benefits, again, when it's talking about carbon chelated, right, humate fertilizer that we have, it's not only the secondary and micronutrients that are carbon chelated, but it's also the nitrogen, the potassium, and the phosphorus, right? So what that does is it eliminates nitrate leaching by improving the CEC and nutrient retention, and by becoming a constitute of the soil organic matter profile, and as opposed to things like nitrates and phosphates, they have a negatively charged ion attached to them, and so they don't bond to positively charged soil colloids, and so they end up into the runoff into our aquifers, and that causes things like algal blooms and a whole bunch of problems down the line. The improved soil aggregation, we talked about that, and water retention, sequester carbon, which also aids. Whenever you're able to sequester carbon or add more carbon into your substrate, you're giving your that system energy, and that energy is going to be utilized for things like phosphorus cycling, nutrient cycling, the nitrogen cycle, the carbon cycle. And so you have to use it as fuel and kind of get that engine running, and once it's going, it gets better and better after time, as long as it's properly managed. But again, I strongly, obviously, I sell humic and fulvic acid fertilizer, a complete fertilizer, but also has more humic and fulvic acid than any other product on the market. So you're getting multiple benefits from it. You're not just getting the benefits of the humic and fulvic acid, but you're getting the benefits of the biostimulating effects of those and the actual complete nutrition, where you're getting the NPK, small amount of secondary, and small amount of micronutrients. All right, let's just talk about some of the key difference. Solubility. Humic acid is insoluble at low pH, while fulvic acid is soluble across all pH ranges. The molecular weight, humic acid has a higher molecular weight, between 3,000 and 30,000 Daltons, while fulvic acid has a lower molecular weight, typically between 500 to 2,000 Daltons. The color is a little bit different. Humic acid is usually a little more dark brown to black, and then fulvic acid has a lighter color, usually light yellow to light brown. Nutrient chelation. So for humic acid, it's strong but less mobile. So it can increase ECE, can hold nutrients for longer, but those nutrients that are attached to humic acid are less mobile. Fulvic acids are highly mobile and excellent at chelation. Humic acid, when it comes to bioavailability, is lower due to its molecular size, and fulvic acid is higher and can penetrate plant cell walls. As far as the interaction between soil, key differences: humic acid enhances CEC and soil structure, and fulvic acid enhances nutrient uptake and stimulates microbiology. And then metabolic activation. Humic acid modulates via surface interactions, and fulvic acid has strong intercellular metabolic effects on plants. So those are kind of like the general key points that I came up with that I wanted to share in my little presentation there. I'm going to go ahead and open this up to the Q&A section, and I'll kind of come here and scroll through some of these comments in case I missed anything. Zach says that it's a day late on his GMO. Well, they'll be fine in the dark. It's better to have them in the dark than just in the light. But just make sure that you get them into a high humidity environment when you receive your clone. And if you have any issues, just hit me up and I'll take care of you. Here's a good question. Are all humic and fulvic acids out there created equal? Man, that's an excellent question. The answer is simply no. And one of the ways that you can tell is because there are different ways that people are processing. I'm going to give you an example. So if you look at the humic acid that is distributed by, what is it? Not Fox Farm, but damn it, they make all the BioLive and Down to Earth. Okay, so Down to Earth fertilizers, they're humic acid. If you look at the ingredients, it says derived from leonardite. So leonardite is the actual material, but when you open that picture, open up that box, what you're looking at is just crushed up leonardite. So in that form, it's still in its mineralized form, and it's not going to have nearly the same effects, because if you really want to get the effects from that, you have to solubilize. Look, you have to micronize that to increase the surface area. You have to solubilize it, and then you have to change the pH of that material to extract the pure humic and fulvic acid. Because when they're not extracted from the material, that material is going to take, I mean, so long to break down and do all of the things that I just talked about. So nutrient chelation, offering the benefits for, you know, soil structure and water retention. Those things need to be at least solution grade to have a benefit, but they really need to be, you know, extracted. And so not all humic and fulvic acid products are the same, because if you're getting just a dry powdered amendment, like, it's really hard to do pure fulvic acid powder, because it has such an affinity for a water adhesion and water absorption that unless it is completely stays 100% dry, it'll start turning into like an ooze. It'll get all like soft, and like it just turns into like this nasty, it looks like something out of Aliens. And so you can extract pure humic and fulvic acid and then dehydrate it, but it's an additional step, and the best way to do it is to actually extract it from the material. And so there's not, I think, you know, Bioag is one company that has liquid humic and fulvic that they've done through an extraction process. There's a couple other companies, but if you ever buy humic and fulvic acid just for the humic, you know, just for the benefits of those, you want to make sure that you're getting an extract, that it's been extracted. So and the difference between regular humic and fulvic acid and what we have is that this is not just humic and fulvic acid, but it's complete fertilizer. That's why it works so well on crops. Any issues using 1 teaspoon per gallon of the complex listed foliar dilution with the 1 tablespoon of you can mix it. All of our products that we have at Bokashi Earthworks can be used in conjunction with each other. They're cross-compatible with a lot of other nutrient brands and lines, other microbes. Okay, here's the question. Yeah, you can mix the dilution ratio with Epsom salt, but 1 teaspoon per gallon of the complex is fine with, you know, 1 tablespoon of Epsom salt. It'll actually help create better bioavailability, again, because anytime you're putting like a nutrient that is soluble, that's going to create soluble nutrient ions that can bind with that fulvic acid in solution, is going to create better bioavailability. That's one of the reasons why the humic and fulvic acid fertilizers work really well with salt-based nutrients, because what happens with salt-based nutrients, when you put that salt, it completely dissolves, and what's happening is those nutrient ions are disassociating from each other. So if you have something like DAP as your starter, diammonium phosphate, the ammonium is detaching from the phosphate molecule, and those are soluble in solution, but they're also highly reactive, and so they can bond, like phosphate can bond with calcium or magnesium at higher pHs, and it can bond with most of the metal alloy micronutrients, metal alloyed micronutrients at lower pHs. So because of those precipitation reactions, they can become the use efficiency drops, you know, because the plant doesn't have available, you know, those nutrient ions become unavailable. And so when those nutrient ions are in a solution with fulvic acid, the fulvic acid will bond with those nutrients, and so when it delivers those, it delivers those nutrients more efficiently, and it increases the efficiency of those nutrients, because it's stopping the precipitation reactions that are happening from those, you know, dissolved nutrient ions that are in solution. Let's see. Badger says, you mentioned that applying spores after rain helps combat and outcompete pathogens. But are we able to apply it to the buds even if it hasn't rained? Yeah, I mean, that's the benefit of all of the spores, which we will be back in stock in about a week. The Mendo Dope Boys did an episode and we got wiped out after that. So, the thing is, there's no carrier. It's pure spores. So it would be the equivalent if you were to, just put water on your plants, like if it was going to rain. So if you go in there and you're lightly spraying down your plants while they're in flower, look, if you don't have to, then don't. Like, I don't want to spray in flower at all if I can avoid it, but out here outside, I can't avoid not spraying. I have to spray outdoors because we have so much insect and pathogen pressure due to our environment out here. So I have to be diligent about continuing spraying even in flowering outdoor. But again, it's not harming anything because there's no carrier and it's not going to leave any type of residue and it's not going to have any negative impact on the way that the bud is flowering. It's not going to create mold and pathogens. It's going to prevent all those things. If you apply trichoderma with a food source, is it better for colonization? It depends on if you're an inert substrate. So let's say you're just in an inert cocoa media, it would be beneficial to add a little bit of a carbohydrate because you don't have a lot of soluble organic compounds to feed on. Now, if you were to add like soil amendments and compost and all that stuff already in your media, then I think adding a complex carbohydrate to the microbial inoculation is probably overkill, because what's going to happen as soon as you inoculate, they're going to go to work and they're going to start proliferating as long as they have access to adequate carbon, nutrition, and water. Badger says, am I able to use the Micro Plus on my clones before they shoot roots to inoculate the medium with good bacteria? At what rate would you make the solution? So if you wanted to do something like that, I would actually recommend using the Bacillus subtilis as opposed to the Micro Plus. If you were doing soaking for seed germination, Micro Plus, Bacillus, Trichoderma, they're all good. But Micro Plus has some, saprophytic microorganisms, and you don't want to use it until you pop roots, because you can colonize the roots once you have it. But look, I don't personally use it. I've seen people that have done it, but in that type of case, I would probably use the Bacillus subtilis over anything for like the rooting stuff. Yeah, spores are excellent. We'll do some episodes on that. Today I wanted to talk about the humate fertilizer. Another thing that is important is that, these formulations work in different types of settings, but it's up to you to figure out. Like, we make recommendations on feed charts, and we're actually updating those, how you want to feed, because you can use it as an additive even though it's a complete fertilizer. So you may only need to use it one time in veg, one time during transition, and one time during flowering, once a month, So you may only be feeding your plants, 3 times during a whole cycle. But if you're in an inert media, or if you don't have a lot of soil nutrition, you might apply it more frequently. So it's, contingent. But the cool thing is that these organic products are 100% water soluble, and they're going to work immediately. So if you are experiencing issues and you need to fix something fast, but you're in a setting where you're like, well, I'm in, living soil or whatever, you can use these products to hit them, get them what they need, and get them out of the slump. But we have right now Micro Plus, the N-Humate, Green Bodie amendments are 20% off on the Bokashi Earthworks website. You can check that out. I'll drop a link in the chat. So I'm going to end the live now. I appreciate everybody coming by. Go check out the website, and we'll keep doing this. I'll keep running cool topics and going over all the information that I can kind of free flow from my brain. So peace out, everybody. I'll see you guys soon.